Today we're going to talk about the fundamentals of polymer chemistry for the Chem 312 lab. What is a polymer? How do we draw them and represent them? And what can we glean from the structure of a polymer in its applications and use? So first, let's start with what is a polymer. Well, the word polymer can be broken into two parts, poly and mer. Now, mer we've already seen. If we go back to isomer in our first week, we saw that mer meant unit or part. Now we're looking at adding in that piece of the word poly, meaning many. So if we, at its most basic definition, a polymer is something that's composed of many units or parts. Polymers have what we call a repeating unit, something that occurs over and over and over again in their chemical structure. And these units are called monomers. Mono meaning single, mer again meaning unit or part. So these polymers, right, are these long chains, these molecules that have long numbers of repeating units, and we have to have a way that we can draw and condense these structures because polymers can easily have molecular weights in the thousands and hundred thousands of grams per mole, and so it would be very hard to draw that kind of a structure. So the first polymer that we have here is polyvinyl chloride, PVC. Right? And this polymer is constructed from vinyl chloride. That's where the name comes from. It has this long repeating chain, right? This is a vinyl polymerization. Be sure to look in the PDF for some more guidance on this and practice on where this structure comes from. Whenever you see a long chain of carbon atoms on the backbone, right? So here we can see that this is entirely carbon atoms along the chain itself. That's going to be a vinyl polymerization. And so what we do is instead of drawing out the entire molecule, we have this notation that uses parentheses and this little subscript n to describe that this unit is repeating over and over and over again. So there's other types of polymers. There's not just vinyl polymers. We also have another example we're looking at actually this week is the synthesis of nylon. This is what's called a condensation polymerization. Well, this one's not exactly condensation because we're not losing water, but it's close enough. And here we have amines, right? So we have this NH2 that reacts with an acid chloride. That's the name for this functional group. You will see that in lecture later on this quarter to get this nice long repeating chain. And here we can see that we actually don't have entirely carbons along our backbone. Right? We also have nitrogens along there. And so this is probably not the same as that vinyl polymer that we looked at before. And we can break down this repeating unit by just drawing out the chain that came from our acid chloride and the amine. So there's lots of practice for this that's in your notebook. And you also are going to get some time to think about this for a few other examples. So a few other examples of these kind of condensation-like polymerizations. Again, we have nylon, but Kevlar and Nomex are two other commercial fabrics and materials that use a very similar polymerization method. However, they just use different monomer units, right? So Kevlar, we have these nice aromatic rings, and they're nice and spread out. We know that this is the component in bulletproof vests, right? This is a very strong material. Nomex is, again, a very small change in the structure of this polymer, but Nomex is actually a fire-resistant material. And so the way that the polymers are built impacts their physical properties, right? That's one of the big ideas of chemistry is that the way something's assembled impacts what it can do and how it reacts. Polymers are no different. So polymers can be built in a few different ways. So the first we're going to talk about is step growth polymerizations. So these are condensation polymerizations primarily, or at least that's the ones we are going to be looking at. So very much like the Nomex and Kevlar and nylon reactions, these undergo what's called a step growth polymerization. And the way we can think about this is kind of like building with Legos, where we have all of our individual monomer units, and whenever they bump into a component they can react with, they grow in these kind of chunks, right? So we can build into groups of 2 and then groups of 4 and groups of 8. And so step growth polymerizations kind of grow in chunks. The alternative is what happens with the vinyl polymers like PVC. These are what we call chain growth polymerizations. And you can think of this like adding pearls to a necklace. It's very slow and methodical, right? We're adding one monomer unit at a time. We're not growing in chunks. And so we start with a single unit, and one by one, right, we grow along this chain. This leads to a much more uniform synthesis of a polymer, but it's not necessarily saying that one is better than the other, right? The way a polymer is built impacts its physical properties, and sometimes we might want a different range of physical properties, right? So we can continue to see how these chains grow. So we can actually alter and control these physical properties of polymers, right, by changing the monomers, but we can also change the physical properties based on how it's built. So if we can control the molecular weight and the topology and the composition, we can actually change what a polymer can do. So the molecular weight is really just, you can think of this as like the chain length, right? Long chains, short chains, medium length chains, all of these will impact the physical properties of the polymer, right? Some of them might be more brittle, right? If they have these kind of more short chains that are stuck together. And some might be a little bit more malleable or flexible if they're long chains that can bend and flow around each other. Another thing that we can alter is the way that these polymers are connected and how they interact with each other. So if we just have a simple linear polymer, right, one that's just a nice long chain of atoms, that would react differently than polymers that have what we call significant amounts of branching. So different ways in which it grows out from that central chain. Generally, more branched polymers, polymers that have a greater network of branching, will have more or stronger physical properties, right? So there's different options here in terms of the way that these chains can grow and expand. Lastly, the composition also is another way we can control the way a polymer reacts and its physical properties. So we have a number of different examples that are shown here, and these are, just think of them as the repeating units. So we can actually change the repeating units in the middle of a polymerization, and we can start to get various compositions of our structure. And so the way that these monomers are built, so the way that they're assembled, can also impact their physical properties. So those are just a few ways that we can alter the way a polymer will behave. So what are we actually going to be seeing this week, right? So this week we're focused on the use of two different polymers. So the first one is we're going to be looking at how we can make silly putty and slime using polyvinyl alcohol. And so here, the polyvinyl alcohol is, again, this long chain that has these alcohol sub or groups that are hanging off of that carbon backbone. And they can participate in something that's called cross-linking when you add in borax. So this boron oxygen compound here is something called borax. And what this does is this actually causes our polymers to cross-link, right? So they kind of get tangled together. And that makes it go in, or that gives it a little bit more strength. And it gives it a little bit more shape. And so this is how we can actually make silly putty and slime using this polyvinyl alcohol. And the reason that silly putty and slime can stretch and move is because this boron atom can actually swing around between these different oxygens, right? So that crosslinker can break and reform. That's why if you take silly putty and set it on the table in a nice ball, it'll sit as a ball for a second, but over time it starts to spread out because those crosslinkers are breaking and reforming. The other thing we're going to look at is uses of polyacrylic acid. So this compound has these carboxylic acids on the side chain, and we're going to look at three different applications of polyacrylic acid. One is in water absorption, right? So this is a highly polar functional group, and it can hold on to a lot of water. Because of that, it has applications in things like diapers that need to hold and store a lot of water. It has applications in the synthesis of something that's called fire gel, which is gel that heats very, very slowly because it contains a tremendous amount of water. It can also be used to pull metal ions out of a solution, right? So you could clean up a metal spill using something like polyacrylic acid, because these metals would then get captured by all these different functional groups. So we're going to see these in the demonstration video. This is just the fundamentals. Thank you.